All right, section 2.1 is dealing with density curves and the normal distribution. Often we want to model distributions of numerical data sets mathematically or study them on a more theoretical level. In such cases, it's convenient to fit a smooth curve to the data set. To the right is an example of how a smooth curve can be fit to a data set. I think these were the heights of like 150 students at our high school. And as you can see, the histogram's got spikies, but there's a nice smooth curve fit to it. Notice the curve doesn't fit perfect, but then again, nothing in statistics fits perfect. We are simply using a simplified model to approximate the distribution of data. If this smooth curve is scaled so that the area under the curve is exactly 1 or 100%, then the curve is called a density curve. So if I were to look at the area under this curve, it would definitely not be equal to 1. But if I scaled the y-axis differently, I could create a curve so that the area underneath it is exactly equal to 1, and that would be a density curve. A density curve has two properties. First of all, it always has to be on or above the horizontal axis, so you can't have negative probabilities. Always has to be above, and the area underneath it always has to be equal to 1. So if I could make some kind of weird shape, however I wanted, as long as the area under this thing is equal to 1.0 and it's above the x-axis, it's a density curve. A density curve describes the overall pattern, much like the shape. And this is kind of another key point here. The area under the curve and above any interval of values on the horizontal axis is the proportion of all observations that fall in that interval. So what that's saying is, if I find the area between 7 and 9 on some density curve, that area, the percentage of that area, so like maybe it's like point, I don't know, 42. That corresponds to the percentage of the data points that are between 7 and 9. So that's kind of a nice property. If we find the area under this fancy looking curve and it's 0.15, that tells us that 15% of our data points were between 63 and 66. Example, finding the height of a density curve. Not all density curves are smooth bell-shaped curves like this one. To the right is a density curve for some distribution. For this distribution, 47.1% of the data are between 8 feet and 10 feet. 5, 6, 7, 8, 9. So between 8 and 10, that's exactly 0.471. Well, if that's the area to the right of this bar, and this thing has got to add up to 100%, then this has got to be the complement of that, 1 minus that. So that'd be 529. 1 minus 0.471. So this area has got to be 429. The nice thing about this one is this is just a rectangle. Well, it looks like a square, but it's not. A rectangle that's got this dimension is 1, 2, 3 feet, and this dimension is h. So the area of a rectangle is length times width. That's got to be 529. So h has got to be equal to, let's go approximately equal to 529 divided by 0.529 divided by 3. 0.1763. 176. So there we go. That's the height. That's the height that will make this thing a density curve. Find the probability that x is between 3 and 8. Okay. Let's find 6 and 8, sorry. Let's find 6 and 8. 6 is right here. 8 is right here. So I want the area of this. Well, this has got a width of 2, and its height is 0.176. So the probability that x is between 6 and 8 is 2 times 0.176 times 2. 352. Let's just say about 32%. This is about 32%. Find the probability that x is exactly equal to 7. All right, so this is a little bit of a tricky question, kind of a theoretical question. 7 is right here. So I want the area below 7. Well, this is just a point, and as we know, points don't have any width, so the area underneath a point would be equal to 0. And this actually is equal to 0, if you can believe it. It might not sound sensible, but remember, this is a continuous distribution. You could have a point that is 6.99991321468, right? And another point that is on and on and on. 7.000112101, 31. So when I ask you what's the probability that x is exactly equal to 7, I'm asking you what's the probability that x is equal to 7.000000 with infinitely many zeros after it. And in a continuous distribution, the probability of getting 7 with exactly infinitely zeros, it's nil. It's impossible. So in a continuous distribution, the probability of getting any one value is equal to 0. Okay? IQ scores are often modeled with the following density curve. Note that the area under the curve from an IQ of 110 to an IQ of 130 is 0.23. Interpret this value. Well, this is a density curve, so the area under the whole thing is equal to 100%. Therefore, whatever area this is, that's going to represent the percentage of people that have that IQ. 23% of people, I don't know what people they're talking about, but have an IQ between, 110 and 130. Okay? One special type of density curve is known as the normal curve. By the way, this is a picture of kind of the normal curve. It looks kind of like that. It was discovered by Carl Friedrich Gauss. You've heard of Gauss before, probably, with some matrices and stuff. It's the same Gauss. Same Gauss that had the story about counting the first 100 integers or whatever. As he furthered the research of others who observed that human errors in measurement followed a certain curve that is unimodal and symmetric. He was looking at people making measurements. Usually their measurements were pretty close to the actual measurement. But he found that they weren't always right. Sometimes they were off by a little bit. Oftentimes they were off by a little bit. Infrequently they were off by a lot. But after looking at many, many data sets, he found this kind of normal distribution. It is well known that many distributions follow this normal curve. So here's the formula. Now the formula looks pretty complex. This is a formula where the mean is equal to mu and the standard deviation is sigma. So it's 1 over sigma times the square root of 2 pi. I like how it shows pi and the natural number e. That's kind of nice to see in statistics. X minus mu negative. The thing that should be kind of impressive about what Gauss did was not only did he find a curve that looks kind of like this, but he found a curve that when you go from negative infinity, because this curve never touches the horizontal axis, when you go from negative infinity to positive infinity, that area, that infinitely long area to the left and right, adds up to exactly 1.0. So if this thing looks kind of crazy, well, the impressive thing about it is when you plug in these values, the area underneath it will always be exactly equal to 1.0. So I'm asking you guys to graph the curve on your calculator with a mean of 0 and a standard deviation of 1. That makes it the standard normal z curve. And then use your calculator to find the area from 0 to 1. All right, so let's take this equation and plug in f of x equals. So let's plug in 1 for the standard deviation. So this simplifies to just 1 over square root of 2 pi. And this is e to the, we're putting in the 0 for the mean. So the top is just negative x squared. And then the bottom is just 2 times 1, so 2. So if we put in 0 and 1, it cleans it up quite a bit, makes it look a little better. Let's just graph it, see if it looks right. So we got fraction 1 over square root of 2 pi. I think it's just neat how the natural number e and pi show up in this seemingly something that's unrelated to circles and also unrelated to exponential growth, kind of. X squared over 2. Can't see it real well because it's so low, but the reason it's slow is because the area from negative infinity to positive infinity under that thing is exactly equal to 1. So let's do a zoom box around it. Oops, what'd I do? Menu, zoom box. Let's go from about right there to maybe about right there. Escape. Okay. So I want to find the area under this from 0 to 1. It's kind of hard to see where 1 is. Let's scale that axis so there's a tick mark every 1 unit. Let's set the X scale to 1. All right, so I want to find the area from 0 to 1. So this is actually kind of a calculus thing, finding the area under weird looking curves. It's called an integral. Now in calculus, even once you guys learn how to find integrals, you're not going to be able to find an antiderivative of this thing. I don't think an antiderivative exists, but we can do it numerically, and there's techniques for doing it numerically. But you don't need to know how to do this. This isn't part of the class, but if we find the integral from 0, so for lower bound I'm going to put in 0, and this is kind of nice. I can kind of move this thing and see right there, you can see the area. So basically I kind of, as I go to 1, looks like it's about 0.3, 0.34, 0.35. But if you keep going, 2 standard deviations, 3, so we get 0.499, 499, 499, and eventually it'll go to 0.5, but that's just rounded. It's 0.4999, 0.499999, and as we go to infinity, we collect exactly 50%, and then the other 50% is over here. So it looks like it's working, but for the upper bound, I'm just going to put in another 1 here, 1. So about 4, and we can get more accurate if we click on that thing and hit the plus button, get more accuracy, but about 0.341. So if I wanted to write that mathematically, this is a z distribution. The probability that z is between 0 and 1 is 0.341. All right, explore the applet located at blah, or Google the practice of statistics. This is an applet from our book. Go to statistical applets, normal density curve. Explore percentages informally when you have a mean of 0 and 1. Kind of like I just did right there, only this has got some sliders so you can just kind of click on the buttons and move them around. See what percent is between 1 standard deviation below and 1 standard deviation above. How about 2 below and 2 above, 3 below and 3 above, 4 below and 4 above? And just play with it and kind of observe. Then you can actually change the mean and standard deviation to match these IQ scores. I think this had a mean of 0 and a standard deviation of 15. It doesn't even really say that, sorry. So if you want to put in some actual values, put in a mean of 100 and a standard deviation of 15, okay? All right, we'll start here tomorrow and discuss this, or you can watch the next video. Thank you.